So we're in 14.5.
Feel the need to comment on my body every single day.
Whoa.
Dylan.
Every time you're like, on your feet, Dylan, back up.
All right. Let's focus on math, please. So what we want to do is we have a surface. Z equals f of xy. Whoops, z equals f of xy. And we want to find the surface area that's above a region R in the xy plane. So here's a picture. And this is our starting point for how we're going to set this up. Here is our function up here. There's z equals f of xy. And what we're going to do is divide this into little parallelograms, or little rectangles. And we're going to call this point at the corner of this little rectangle P of ij. P sub ij. That's just that point. And we're going to call the area of this is delta S sub ij. And if we project this down into the xy plane, we have a point down here, x sub I, y sub I. Sorry, that would be y sub j. Down in the xy plane. And in the xy plane, we get little rectangles when we project that down into the xy plane. And in the xy plane, this side of the triangle is going to be delta y sub j, and this side of the little rectangle would be delta x sub I. And what we want to do is sum all of these little delta s sub I j's over the surface. So what we're going to do is take a look at a little portion of a tangent plane at that point. So we're going to construct a tangent plane at P sub ij, and we're going to approximate the area of the surface with the area of the tangent plane at that point. And we're going to make delta x and delta y very, very small. So that's our starting point. So we're going to approximate delta S sub ij with the area of a portion of the tangent plane. At P sub ij. So I'm going to draw another picture on the next page, and we'll just draw the portion of the tangent plane. All right, so we're good with the idea here. Okay, so here is our, I'm going to also kind of, I'm going to magnify this portion. So here is P sub ij. And we're going to construct vectors that are parallel to the x-axis. So I'm going to call this vector A. And vector B that's parallel to the y-axis that are adjacent sides of that little piece of the tangent plane. So if I extend this over, we get a little parallelogram. And the area of this portion of the tangent plane we'll call delta t sub ij. So A and B are adjacent sides of the portion of the tangent plane. At P sub ij. And if I project this down into the xy plane, like so, we're going to call that's not very parallel to the x-axis. We're going to call that length delta x sub I, and I'll project this down, and we'll call that length delta y sub j. And we could, so there's that portion of the tangent plane projected down into the xy plane. All right, so we can represent these vectors that are parallel to the x-axis and the y-axis at P sub ij. We can write our vectors in component form. A is going to be delta x sub I hat, plus f sub x at x sub I, y sub I. That's our rate of change, our slope, times delta x sub I. That's how much that vector goes up in the k hat direction. So we're just thinking, this is a little piece of a line. We go delta x sub I in the x direction, and we go this much in the z direction. And vector b is going to be delta y sub j hat, plus f sub y, the partial with respect to y at that point, x sub I, y sub I, times delta y sub j k hat. That's how much it goes up or down as we move along delta j directions, or delta j units. We can find the area of that parallelogram by the magnitude of the cross product of those vectors. Delta t sub ij is the magnitude of A cross B. So we're taking the magnitude of that cross product to approximate the area of that portion of the tangent plane. Well, A cross B is, we can find it using this determinant, I hat, j hat, k hat, delta x sub I, 0, f sub x at that point, and then we have a 0, delta y sub j, f sub y at our point, times delta y sub j. And when we cross that, when we take that cross product, we get these products, delta x sub I, delta y sub j, that we can factor out. So I'm going to call delta x sub I, delta y sub j equals delta A sub ij. Just a little piece of area, delta x, delta y. When we do this cross product, we get that this equals minus f sub x, x sub I, y sub j at that point, I hat, minus f sub y at that point, x sub I, y sub j, j hat, plus 1 k hat, and we have this factor outside delta A sub I j, which is delta x sub I, delta y sub I. And the magnitude, the form that this takes shouldn't be a giant surprise at this point. is the square root of f sub x at x sub I, y sub I, sorry, y sub j squared plus f sub y at that point, x sub I, y sub j squared plus 1 times delta a sub ij. And the total surface area comes from summing those little delta a sub i's over the surface. We take the limit as delta x sub I, delta y sub I approach 0, like we've done before. And we get the surface area of that surface. So I'm going to say in the limit I'll go back in just a second. Our surface area S, I'm going to use a capital S, S equals the double integral over our region of the square root of f sub x squared plus f sub y squared plus 1 dA. And often you'll see this written as the integral over our region, double integral of ds. And this is very similar to our integrand for arc length in 2 dimensions. It's very similar to our integrand for arc length when we talked about curvature. And what other quantity is given by f sub x, a vector f sub x I hat, f sub y, j hat, 1, k hat that we've talked about? Isn't that the normal vector to a surface z equals f of xy? So really what we're doing is integrating the magnitude of the normal vector of that surface over the entire surface. So the magnitude of the normal vector is telling us something about the area of the surface. The magnitude of that the magnitude of the cross product as an area is what we're integrating. So that idea that the cross product, the magnitude of the cross product gives us an area, turns out not to be just kind of an interesting thing, but an essential thing for what we're going to do here, and we'll use that quite a bit in chapter 15 when we talk about surface integrals. Mm-hmm. And as you might guess, because of the form of the integrand, surface area integrals typically are not very nice. All right, we good? So keep this idea in the back of your head that this quantity, square root of x, f sub x squared, f sub y squared plus 1 square root is the magnitude of the normal vector at a point, because that in chapter 15, when we come back to the idea of a surface integral, that idea will be pretty important. All right, so I just want to go through a couple of examples of setting these up. Now the problems that we'll do that you have to evaluate by hand tend to be not contrived, but they're set up so that you can simplify them so that they're doable. Often the surface area integrals are very difficult. So it's just another way, another quantity that we can put in our double integral and integrate. So another interpretation other than volume under a surface. All right. We want to find the surface area of f of xy equals 10 plus 2x minus 3y, bounded by our region is all the set of xy such that x squared plus y squared less than or equal to 9. So that, just by the way, that's how you read that. The region is all xy so that x squared plus y squared is less than or equal to 9. The colon means so that or such that. Well, this one's not too bad. Our f of xy here is not a complicated function. What is this? A plane. What is this? A circle. So in 3 dimensions, it would be a cylinder. So we have a plane slicing off a portion of a cylinder. So similar to our integral of the day, except instead of a volume, we're finding a surface area. So f sub x, partial with respect to x is nice 2. F sub y is -3. Based on this region, how do you think we want to set this up? We could let x go from 0 to 3. Would it go from 0 to 3? Or our region would be this. So if we did vertical rectangles, y would go from negative square root of 9 minus x squared to positive square root of 9 minus x squared. So that would be a trig sub, right? So since it's a circle, let's use polar. I would say use polar. So our surface area is going to be the integral from theta goes from 0 to 2 pi. Can we just divide this by 4 and go from 0 to pi over 2 and multiply by 4? Are you sure? It depends on how the plane is intersecting the cylinder. I would say probably not. I'd say probably not. And we're going to go from, radius goes from 0 to 3. And our integrand is the square root of 2 squared plus -3 squared plus 1 r dr d theta. So that's nice and easy. 0 to 2 pi, 0 to 3, square root of 14, r dr d theta. And that gets us 9 square root of 14 pi. And this is one where we could say, well, the theta integral, there's no function of theta here. So the theta integral just gives us a multiple of 2 pi. So we could integrate that right away.
So what was that? That's just where is the plane?
The plane is up here, and I don't know exactly how it slants, but it'd be kind of a slanting plane slicing through the cylinder.
Would we be responsible to figure out how to illustrate that?
No. Just, I think it would be good to be able to kind of conceptualize it.
Simple pictures,
Right.
like there's a plane somewhere.
Right, slicing a cylinder.
Okay.
All right, so I want to do one. Is this? Yeah. Let's do this one. A little bit less, but not too bad. Let's find the area of the cone is equals to square root of x squared plus y squared inside the cylinder x squared plus y squared equals 4. So what we have here, just a quick sketch. We have a cone, like so. There's z equals 2 square root of x squared plus y squared. And we have a cylinder that is slicing the cone. Let me redraw that just a little better. There we go. So there's a cylinder slicing through the cone, like so. And we want the area of the cylinder that's inside, or sorry, the cone that's inside the cylinder. So we're talking about the area of this cone inside the cylinder. So for this one, for these types of integrals, like we had on the integral of the day on Friday, part of the problem is deciding, well, what is your function and what is defining your region? So the region in our xy plane is x squared plus y squared less than or equal to 4. So the cylinder is what defines our region in the xy plane. And our surface is the cone. So we want, and it asks us to find the surface area of the cone. So that's our going to be our function that serves as our surface for our integrand. The other piece gives us our region in the xy plane. All right, so partial with respect to x is 2x x squared plus y squared to the minus 1/2. And f sub y is 2y x squared plus y squared to the minus 1/2. And this integrand, the square root of f sub x squared plus f sub y squared plus 1 is this quantity. It looks not very nice. 4x squared over x squared plus y squared plus 4y squared over x squared plus y squared plus 1. Do we see how this simplifies? We have a common denominator.
You can factor out 4.
So when we have our common denominator, we get x squared plus y squared over x squared plus y squared. Well, how many x squared plus y squared does that give us in the numerator? 4x squared, 4y squared plus x squared plus y squared. 5x squared plus y squared. But what is our common denominator? X squared plus y squared. This is square root of 5.
Of course.
Find the common denominator.
It's so simple.
Our numerator becomes 5x squared plus y squared. Our denominator is x squared plus y squared. The x squared plus y squareds cancel. This thing that looks really bad turns out to be really nice. And our surface area is going to be the integral from 0 to 2 pi. The integral from 0 to 2, square root of 5, r dr d theta. I didn't evaluate this one.
Oh my goodness.
Yeah, left to the reader as an exercise. It should be like similar to the last one. So what do we get? 2 pi square root of 5 times 4, 2 squared over 2, 4, 2.
2.
So we get 4 pi square root 5.
Right.
Is that right?
Which is what I said, Dylan.
Is that what you said?
Yes, Dylan. Don't give me that weird look.
I think that's right. Yeah. Yeah, this one turns out to be a nice integral to evaluate. Let's look at one more and then I have some questions for you. We're finding the surface area. Of the portion of z equals 16 minus x squared minus y squared in the first octant. So what is this thing? Paraboloid, right? And we have 16 minus x squared minus y squared. So it is, how is it oriented? Downwards. So if we drew a picture, it would look like that. Ish. This is kind of a pointy paraboloid, but. And this, we're in the first octant. What is this thing?
That's a circle.
Circle. What is the equation of the circle? X squared plus y squared equals 16. So our region in the xy plane is the circle x squared plus y squared equals 16. So how are we going to want to set this one up? Polar. This our region is a quarter of a circle. This is our function, z equals f of xy. So f sub x is minus 2x. F sub y minus 2y. And our integral surface area is going to be the integral from 0 to pi over 2 in the first octant, 0 to 4 for our radius, and we have square root of 4x squared plus 4y squared plus 1, r dr d theta. We need to express this quantity in terms of polar coordinates. And we get the square root of 4r squared plus 1, r dr d theta. Nice u sub integral. I didn't evaluate that one either. So it looked like it could be messy, but it turns out really nice. This quantity with quadratic surfaces, you get a square root of an r squared something something, and r dr d theta. That occurs frequently in polar coordinates with quadratic surfaces.
So why is it an increasing number of them are no longer solved?
Setting them up is most of the problem. We all know how to evaluate integrals now.
But do we really?
Yeah. All right, here are some questions for you. We had some similar questions earlier. Z equals f of xy, and this is greater than or equal to 0 over r in the xy plane. So we have a positive function. True, always, sometimes, never. Is it possible for S to equal area of R? The surface area of that function, is it possible for the surface area to equal the area of the region?
Yeah. It's a plane.
Yeah, if it's a plane, right? So yes, it is possible. Yes, so I'd say sometimes. We need a plane parallel to the xy plane.
That's such a good one.
So our surface would be z equals a constant. 2. Can S be greater than area of R? Yeah, mostly, right?
Sometimes.
Right? Mostly.
Because the question is always, sometimes, never.
So usually.
I bet, yeah, 'cause it could be less.
Can S be less than?
What if you were to have like negative?
Surface, and our surface Z is always positive? So can our area of a surface be less than the area in the xy plane that bounds it?
Never.
No.
So this is assuming that you're not going to have like the problem with the integral from Calc 1 where you had negative positive area situation.
Right.
Okay.
It's heard from always, sometimes.
Well, and if we're talking about physical area, then area is always positive.
Possible, frequently, no.
All right, questions?
Yeah, dude. Okay.
Okay.
Yeah.
So hang on, a question about that last one. What would happen if you had a surface that ran out in your area, like the edge of the surface was within your region R?
Oh my god.
Then I would say the problem would have been,
You probably did something wrong?
no, well, either the problem was the question wasn't asked well, or the point was to realize that the boundary, the region in the XY plane that you were given was not the actual boundary in the XY plane. Because you'd have to
Never have to deal with the surface, the edge of a surface in the region.
right, because then the region would be defined by the